Hi everyone, welcome back. Mechanics of Materials, Chapter 5, Torsion. In this example, we have a coder at F which records the rotation at a free ends A in a digital form. The configuration consists of four gears. Two of them has the radius of R and the two others has having the radius of N times R. And they are connected with three solid steel shafts with the same length as you can see here and diameter of D. We want to get a parametric formula for the angle of twist at the free end A. To do so in solving such problems, we will start from the free end like here and get the relation between the gears based off the peripheral motion and also kinematic of a motion between them. And as soon as we get those kind of relation, we can jump to the fixed end at the coder F and start coming forward to get the angle of twist at E, then D, then C, then all the way through B to A. And that's phi A which we are looking for. So let's jump to the problem. The tangential force between the first set of all gears, as you can see, there is the same amount of tangential force between them. So if F is constant, then for gear B, T sub B over its radius is equal to T sub C over its radius. Then we can have the relation between TC and the T which applies to a T AB or TA is equal to the same amount of T, the same amount of torsion is transmitted to gear B from the solid shaft A, and this is the relation between TB and TC based off the uh, uh, unique tangential force between them. And now so far we get the torsion in the second gear. So far we had the relation between gear B and C based off the torsional torque applied at the free end A. Now let's jump to the second set. So firstly we do know the same amount of torsion which applies at C, it's directly transmitted to gear at D. So we already calculated this T sub C is 1 over N times the torsion at free end, and TD is the same amount of torsion at C. Mhm. And again, for the second set of our gears, T sub D over its radius is equal to T sub E over its radius, which is R. And then we can get the, if you replace from the top, you can easily get the T sub E is T over 1. The T sub E is equal to T over N squared. Now we get all the relation between the gears from the free end. Now let's jump to the fixed end and get the relation between the angle of twist. To do so, we, we are starting from the coder, which is fixed at F, and phi E over F, phi E angle of twist of E with respect to F is equal to phi E minus of phi F. And because of fixed end, we do know that phi F is equal to 0. Then phi E is T sub E times the length of the shaft, which is here, over Gj. And we already calculated the Te based off the gears relation, and that's T over N squared. So if we replace that in our equation, so far we start from the very uh, from the fixed end of F, and we move forward to get the phi sub E, which is 1 over N squared TL over Gj. Then we are just moving forward toward D, toward C, toward B, and all the way through the A. So based off the kinematic of equal peripheral gear motion at D. We do know this arch is equal to this one due to kinematic of peripheral motion, and that's R d phi d is equal to R e phi e, and that gives us phi d is equal to 1 over n times phi e. We already calculated phi e in previous part, that's 1 over n squared times TL over GJ. If you replace this in this equation, it just gives you phi d is 1 over n cubed over TLGJ. So far, we started from F, came to E, came to D, from F to E to D, then let's move towards C. C with respect to D, C minus phi d, and we already calculate, we already get what phi d is, and phi, that's 1 over n cubed over TLGJ in the last part. And phi c over d is nothing but tc over l over gj, which we already calculated that tc is 1 over n times t at the very beginning of our solution. So if you replace all that back in phi sub c, it just gives you phi c is equal to this equation. From F to E to D to C, now we need to move toward B then A. So using the kinematic of equal peripheral gear motions, this time for gear B and C. We already calculated what phi C is. The same equation RB phi B is equal to RC phi C, and it just gives us phi B is equal to 1 over n times phi C. And that says if you replace this equation in this one, just gives you phi over phi B is equal to this equation. Then let's start it from F to E to D to C to B. Now let's move from B to A and the problem is over. Phi sub A is phi A with respect to B plus phi sub B. That's TL over GJ, and phi B we already calculated. That's this equation from previous part. Then if we replace all of them back in our equation, it just gives you phi sub A is n to the fourth plus n squared plus 1 over n to the fourth times TL over GJ. And that's nothing but a parametric formula for angle of twist at free end A for such configuration. If we want to put it into an example, we can just simply use the same equation. So if we want to know, if we want to determine, we want to determine the angle of twist at A, when T is 5 pounds, L is 2.4 inches, diameter of solid shafts are 1 over 16 inches, G shear modulus is 11.210 to the 6 pound square inches, and n is equal to 2. So now this time our job is pretty straightforward. This is 5 pound inches. L is provided to be 2.4 inches. Diameter is provided to be 1 over 16 inches. It's supposed to be 1. And shear modulus is provided, and n is equal to 2. So if this is r, this is 2r. Now, because we already know our formula for free end from parametric solution, we can simply first calculate the j base of diameter, turn it to radius and calculate it, and that's this number, and then simply jot down that in our parametric equation. And be careful, phi sub a is in terms of radian. You have to multiply this number with 1 over 80 over pi, or 200 or 360 over 2 pi, to get it in terms of in terms of degrees, and then it just gives us phi a is 53.8 degrees in rotation due to such configuration. Thank you. We'll solve more more problems in torsion. Thank you.